Good morning. I'm recording this on Friday, and I have had so much technical difficulty. I'm even trying to voice text when I'm speaking to you. So I'm hoping today goes well for us on this video. So we're going to finish up section 2.5, and you can write this or not. Let f of x be a polynomial function that has real coefficients. So real numbers are multiplied by our x variables. If a plus bi, where b is not equal to 0, so if you have something like 4 plus 8i, and this only works as long as the coefficient of the I, the imaginary part, is not equal to 0, then a minus bi is also a 0 of the function. The reason this can't be 0 is because then this would just be 4. And 4 wouldn't have a conjugate. It's just one term. We need two terms in order to be able to do conjugates. So that's why we need this little part here. But that's important. That means, and I feel like we might have said this before Christmas break also, zeros occur in conjugate pairs. That's huge. If they tell you that x equals 3 minus I, the little speck didn't need to be there, is a 0, then you automatically know that x equals 3 plus I is also a 0 because zeros occur in conjugate pairs. So let's see how this works. Example 4. Find a fourth degree polynomial function. I think my pencil tip was loose, and that's why we're getting all these little specks. Fourth degree polynomial function with real coefficients. So we're going to satisfy the conditions that we just wrote down. That has -1, -1, and 3i as zeros. So here's something to take note. It says find a fourth degree polynomial function, not find the. So that means there are multiple fourth degree polynomial functions that would satisfy these conditions. So we will find one of them. So first off, if these are zeros, that means x equals -1, x equals -1, and x equals 3i are zeros. And before we go too far, let's remember, if one complex number is a 0, then its conjugate is also a 0. So x equals -3i is also a 0. And that is in the form a plus bi. We're sort of looking at 0 plus 3i. And that's why we would also have 0 minus 3i. So that's your positive 3i, and that's your negative 3i. So if these are zeros, then we want to write them as factors. We're going backwards, so we're going to, the factor would be x plus 1. What we did, just to show all the steps, would be we added 1 to both sides to get x plus 1 equal to 0. But we probably won't do any of those steps. We'll probably just say if x equals -1, it came from x plus 1. For the next x equals -1, it also came from x plus 1. And you could write x plus 1 squared, but we're going to multiply these out, so maybe it's nicer to go ahead and see them side by side. For the third one, it's x minus 3i, and for the last one, it's x plus 3i. Now, I highly recommend that you group these like with like. So let's group those together, and always group conjugates together if possible, so that you can just do a squared minus b squared to get your answer. So right here, we're going to FOIL And we get plus x and plus x, so that's plus 2x plus 1. Write it down in combined like terms if you want. And then for these, all we have to do is a squared minus b squared. All right, I can't simplify anything in the first one, but in the second one, we've got to remember that I squared is negative 1. So this is negative 9 times negative 1, which would be plus 9. I like to distribute with the smaller polynomial, and then I'll go with the 9. It's up to you, though. As long as you end up getting everything multiplied together, that's all that matters. So it's going with the smaller one. I'm going to get x to the 4th plus 2x to the 3rd plus x squared. And then multiplying with the 9, I get 9x squared plus 18x plus 9. And last, we'll just combine all those like terms. I'll do it up here in this little blank spot. So f of x is x to the 4th plus 2x to the 3rd plus 10x squared plus 18x plus 9. So this is a polynomial that satisfies those conditions. We could get a variety of them by multiplying the whole thing by some constant. But this one's good enough for us, so we don't have to choose some number to multiply through by. That satisfies the conditions. All right, let's try another example. Example 5, find a cubic. Won't write all this down, or you don't have to. Find a cubic polynomial function with real coefficients that has, and in this course we're only going to see real coefficients for these type problems, that has 2 and 1 minus I as zeros. And f of 1 is equal to 3. All right. Lots of important clues there. We're going to look for a cubic function, so the highest power will be a 3. And we have these zeros to start with, and then we'll deal with this new fact. So first off, I'm going to write these as my zeros and realize I will also have this one since they occur in conjugate pairs. And then we'll start out our function, change the 0 to a factor. And this one, when we change it, the 1 changes signs and the I changes signs when they go over there with the x. So it's x minus 1 plus I, and this one would be minus 1 minus I when you change their signs to bring them over with the x. Now the way I like to do this is I definitely want to multiply these together because they're similar to each other, and I'd like to group it this way so that these two terms are actually conjugates of each other. They're both x minus 1s, they're both i's, and they have different signs. So I'm going to start out just rewriting x minus 2 because I want to multiply these two together first. So all I have to do is a squared minus b squared. So when we do that, we're going to have x minus 1 squared minus I squared. Just rewrite x minus 2. And now we do need to expand or write this down twice to FOIL that. So that would be x squared minus 2x plus 1. And I squared is negative 1, so that's minus a negative 1, so that's plus 1. I'm going to write it one more time so I can combine like terms in this second parenthesis. Okay, so I'd prefer to distribute this way. You go about it any way you want. So starting with the x for me, I get x to the third minus 2x squared plus 2x. And then going with the negative 2 minus 2x squared plus 4x minus 4. And then we want to combine like terms. X to the third minus 4x squared plus 6x minus 4. So we have a cubic, so we could check that. We used these zeros, but we haven't done anything with this yet. So I'm going to erase this top here. F of 1 is 3. So just like a second ago, I was telling you how this was one function that satisfied those conditions. And if we wanted another one, we could multiply it by a. So we're going to do that step now. We're going to multiply the whole function we just found by a. And we have an xy, we have an ordered pair here. This is f of x, so x is 1. And f of x is always y, so that means y is 3. So we have this ordered pair sitting here in disguise. And we're just going to plug that in for x and for y. So f of x is y, so that's 3. Leave your a, and plug in 1 for all these x's. You didn't have to show all the work like I am. You could have written down what you would get and saved yourself a little time. So that means 3 equals a times 1 minus 4 plus 6 minus 4. That means 3 is a times negative 3 plus positive 3, negative 1. You make sure that's right. And then divide both sides by negative 1, and you get negative 3 to be a. So you're almost done. These are sort of long problems sometimes. Your final answer that satisfies all the conditions is we're going to put that negative 3 right here. I'm just going to rewrite that whole thing, but put negative 3 there. Negative 3, parenthesis, x to the third minus 4x squared plus 6x minus 4. And if you want, you could distribute it, but I'm going to stop there. All right, let's see what else we need to do. Okay, this is just some terms that you need to be aware of. I don't know if you went over these terms last year or not. So if we have, let's just hit some terms. A quadratic factor with no real zeros that's said to be prime, or it's irreducible over the reals. So I'm going to be real upfront here. This isn't terribly important to me as far as the things that are important to me in this course, but it could happen that you, especially juniors, might see this on an SAT or an ACT question, and if we go over it and you remember it, then you could get an extra point or so, and every point matters. So what does that mean? And seniors, depending on what you take next year, your course might cover this. It might be important to your teacher. So it's good for us to see. I'm just not going to test you over it. What's a quadratic factor with no real zeros? Well, it's something like x squared plus 4. If that's a factor of our function, and we want to set it equal to 0 to find our zeros, and we minus 4 on both sides, and we take our square root, then we get plus or minus 2i for our zeros. These are not real. That's why a factor such as this is said to be prime, won't break down more into real factors, or it's irreducible. It's not reducible over the reals. I can't break it down and get real answers. Then the book says, be sure that you realize that this doesn't mean it's irreducible over the rationals. Real numbers include the natural numbers, the whole numbers, the integers, the rationals, and the irrationals. What they don't include is the imaginaries. That's why getting this imaginary answer meant it wasn't reducible over the reals. But irreducible over the rationals just means we can't reduce it and stay in the rational numbers. So we would reduce it and we would get some type of a square root. So an example of that might be the factor x squared minus 2. That's a quadratic factor. We try to set it equal to 0 to find our zeros. We add 2 and we do our square root, and it's not a rational number. It's a number like pi. Anytime you get a square root of a number that's not a perfect square, like 2, then it's a non-terminating, non-repeating decimal. It's 1.17 or 71, blah, 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 and it never stops, never repeats. So it's not rational. I can't take that and write it as a ratio or a fraction. So this one's irreducible over the rationals, and we would need to leave it this way. So the book went on to say one more thing, and they said, even though this is irreducible over the rationals, it is reducible over the reals. Because this square root of 2 is a real number. Okay, so let's see how we do this and how we might encounter a problem like this. Example 6. Write f of x equals x to the 4th minus x squared minus 20, a as the product of factors irreducible over the rationals. Alrighty, so when we look at this function, it's quadratic-like, so I'm going to be able to factor it with x squares. Put my negative 20 at the top and put my negative 1 at the bottom. Factors of 20 are 4 and 5, and they subtract to give us a 1. We just want to make that 5 negative. X squared plus 4, x squared minus 5. We want this to be irreducible over the rationals. So were we to keep going, and we set the first factor equal to 0, we get that imaginary answer. So I can't break this one down and keep it rational. This one, we set it equal to 0, and we solve. Plus or minus. That's not rational either. So the furthest we can go to leave this irreducible over the rationals is this form right here. This would be our answer. All right, B part. Write it as the product of linear and quadratic factors that are irreducible over the reals. Okay, so we had gotten to this step and we had said that this one became plus or minus 2i, and this one became plus or minus square root of 5. And if we want to be irreducible over the reals, we can't break this one down this far because that's not real. But this is great because that is real. Not Israel, but it is real. So we have to leave x squared plus 4 as x squared plus 4 because when we break it down, we get imaginary, and we've got to stop in the real number system. But we can break this down. So if x equals positive square root of 5 and x equals negative square root of 5, then as factors, that's x minus square root of 5, and that's x plus square root of 5. So we can break them down to those factors. These factors are linear because they're like mx plus b. And this is a quadratic factor because it's an x squared. So we satisfied those conditions. Alrighty, example C. Write it in completely factored form. So I just have to keep rewriting, but you don't. X squared plus 4, x squared minus 5. That broke down to plus or minus 2i and plus or minus square root of 5. Completely factored, they don't care if it's real, irreducible over the reals or rationals or anything. So we can call the first one x minus 2i, the next one x plus 2i, the third one x minus square root of 5, and the last one x plus square root of 5. And that is completely factored. All right, one more example. Last but not least, for sure. Example 7. Whoops. Find all the zeros of f of x equals x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60, given that 1 plus 3i is a 0. Okay, so we've been factoring a lot, and we would say, oh, that's got 5 terms. I don't see a GCF, and I don't have a method for factoring something with 5 terms. So I'm going to have to use the rational zero test. But they want us to go a different route. They are going to say, hey, here's a hint. 1 plus 3i is a 0. And we'd say, oh, then 1 minus 3i is also a 0, because they occur in conjugate pairs. So if we take these two zeros and we multiply them together, then we'll get their conjugates, so we can just do a squared minus b squared. And I squared is a negative 1, so that's 1 plus 9, which is 10. That means 10 is a 0. 10 goes into it even. Oh, you know what? I did that wrong. Try to blot that from your memory. I thought, what? 10's a 0? How's that work? I skipped a step. So if x equals 1 plus 3i is a 0, and x is 1 minus 3i is a 0, it means we have x minus 1 minus 3i as a factor, x minus 1 plus 3i as a factor. We'll do that little hint or trick where we group these two pieces together. And now these are conjugates, so we'll do a squared minus b squared. And then we'll expand this to x squared minus 2x plus 1 plus 9. So x squared minus 2x plus 10. If you're confused here, I'm just foiling and combining like terms to get this. All right, that means that this polynomial goes into this evenly because we took two zeros and we multiplied them together. They go into it evenly. Like if you know 3 goes into 60, and I say, hey, you know what, 5 goes into 60, then you can multiply 3 and 5 together and get 15, and you can know that 15 goes into 60 evenly. So that's what we're doing. This is just a number example for you. So we are going to do polynomial long division, your favorite thing I remember before the break. So we're going to set it up, x squared minus 2x minus 10 divided into our original polynomial, x to the 4th minus 3x squared plus 6, whoops, I said that wrong, minus 3x cubed plus 6x squared plus 2x minus 60. And I did check before I got started, 2, 1, none, 4, 3, 2, 1, none. So nobody's missing anything, so we're good to go. What do you multiply x squared by to get x to the 4th? X squared. So then you take it and you distribute to all three of these. So you get x to the 4th minus 2x to the 3rd minus 10x squared. Then you draw your line and you change all these signs. This should cancel every time. That gives you negative x cubed plus 16x squared. Bring down your next term. Then you multiply x squared by negative x to get x to the negative x cubed. Then you distribute it. You get negative x to the 3rd plus 2x squared plus 10x. Draw your line. Change the signs. That cancels every time. 14x squared minus 8x minus 60. What do you multiply x squared by to get 14x squared? 14. Then you take that 14 and you distribute 14x squared minus 28x minus 140. Draw your line. Change the signs. That cancels every time. 20x plus 80. So that's our remainder. Plus 20x plus 80 over x squared minus 2x. Ooh, I made a mistake somewhere. I forgot we weren't supposed to have a remainder. That was supposed to go evenly. Oh, gosh. If we were together, you could have caught me right off. Right here. That should have been a plus. I'm so sorry. So, this sign ends up being a minus. So this ends up being a negative 4. So this ends up being negative 6x squared. So this is a negative 6, which messes all of this up. I'm so sorry. So that's negative 6x squared plus 12x minus 60. Draw the line and change those signs. Looks like something else is wrong. Oh, it also messed this up. That would have been plus 10x, which would have caused this to be plus 12x. draw the line and change all of those signs, and everybody cancels, which means no remainder, which means it went evenly. So now you know that the answer, the x squared minus x minus 6, is a factor, and that breaks down x minus 3x plus 2. So the directions find all the zeros. Well, we got a positive 3, a negative 2, and from the other page, we had 1 plus 3i and 1 minus 3i. And those are our zeros. Sorry, I messed up the long division. Alrighty, that's it for today. I know it was long. I'm sorry, it was just a lot of stuff. See you on Wednesday.